Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Quantum Mechanics 2, with the course code PHY313, we are at the lecture number 13, and the topic is angular momentum and its basic properties. As you know that in classical mechanics, angular momentum is a conserved quantity in a similar way as energy and linear momentum are conserved quantities. By conserved quantity, we mean that when system moves, its property, for example, linear momentum or angular momentum or energy, does not change, they remain constant. In today's topic, we will see that how angular momentum is defined in quantum mechanics and what are its basic properties. But in order to do this, we need some review of angular momentum in classical mechanics. If you recall, then the definition of a angular momentum is equal to r cross p, where r is the position vector and p is the linear momentum of any system which is under treatment. So here we can see that this particle linear momentum is denoted by p, and this is the usual linear momentum, and it is a vector quantity. And then we have this r, which is actually a position vector or a displacement vector from the prescribed origin, because we are dealing all this thing vectorially, so this will be in the some frame of reference. And since these are the vector quantities, so they will have their components. For example, if we are doing this treatment into the Cartesian components, Cartesian coordinate system or rectangular coordinate system, then this linear momentum will have three components in 3 dimensions. Here you can see that p is equal to px, py and pz. So these are the three Cartesian components or rectangular components in 3 dimensions of the linear momentum of the system. And then we have this r also equal is also a vector quantity. So this r also has three components, that is, this is the position vector, so it has the x component, y component and z component. So this is the usual meaning of a angular momentum in the classical mechanics, where it is a vector quantity defined from the position vector and linear momentum vector. So in quantum mechanics, similar will be promoted, but to the operator nature. But in order to define operators, because quantum mechanics is defined by the operators for any observables, so in order to define operators for the angular momentum, we first would like to write it into the components form. To do this, we would have to write the Cartesian components of the angular momentum. So from this equation, that is r cross p, what you can do first is to write it into the determinantal form, that is into a matrix form, and then write in a determinantal form, and then we calculate all the three components of the angular momentum from the left, and from the right you will get some equation like this. So for the x component of the angular momentum, you will find out that it is equal to ypz minus zpy. This is a simple calculation where I repeat again, write r in its components like here, p in its components, and write the determinant, and then open this determinant, and from the first component, that is the x component, you will get this equation. And similarly, you will also get the y component equal to zpx minus xpz, and Lz component equal to xpy minus ypx. It is a good exercise to derive all these three equations. I am sure that you have already done this, but to remind yourself that how this comes about, I would encourage you to derive all these three simple equations for the components of the angular momentum in terms of the position and momentum vectors and operators. Okay, so once we have this thing, we would like to now define the corresponding angular momenta in quantum mechanics. and you know how we do this. In quantum mechanics, whenever we come from classical mechanics to quantum mechanics, the recipe is that promote your observables, some of observables, not all of them. For example, we won't promote mass or time to the operator levels, but the recipe is that promote some of your observables to the operators, because quantum mechanics is an operator mechanics where we have operators for the observables and they act on certain kind of functions. So let's do this and define operators, or to promote the x component of the angular momentum to the operator level. So as we have already defined in terms of Cartesian components, or the rectangular components, that we had ypz minus zpy. So since on the left hand side of this equation, which comes from the first equation from the last slide, you see that on the right hand side we would also have the operators. So y should be an operator, which is a position operator, or the y component of the position operator, and by the way, it would be a multiplicative operator, which means that when acting on certain function, then it will just multiply the value of the position with a function. But on the other hand, this pz is not a multiplicative operator, rather it's a differential operator, and by definition it is equal to minus ih bar del by del z, where del by del z is a partial derivative of that function with respect to z component of the position. And similarly, after the minus sign, we will have the z component of the position operator, and then the py, that is the y component of the linear momentum operator. So by this way, you've seen that how we define the x component of the angular momentum operator, and this is equal to this, which is the combination of the position operator, which is just a multiplicative operator, and the partial differential operator. And here we have partial differential operator because this linear momentum generates translations into the space-time. Okay. Similarly, as we have done with the x component, we would also get the y component of the angular momentum equal to this thing on the right hand side, and it just very simple check that it also comes about with the similar definitions of the operators of z and x, position and momentum, and we get this thing on the right hand side, which is technically or operationally good, because now we know that what to do with the function when Lx or Ly is acting on it. We know that we have to take the derivative with respect to z and then multiply it with the x, and similarly in this term we have to take derivative with respect to x and then multiply with the z, and so on. So operationally this right hand side is needed. Here we have by definition, where we can see that the x and y and the z components of the momenta are in the definition of the angular momentum, but in this term we see how to implement it on certain function. It tells us that just calculate the partial derivatives and multiply with the positions. Okay. Similarly, we can calculate the z component of the angular momentum. Here you can see that this is xpy minus ypx in a similar vein as we have done for the other components. Now question arises, can we combine them? Certainly we can, and we will. If we combine them, what we get is to write them in terms of a del operator. You're wondering what the del operator is? Then here you can see, recall the definition of the linear momentum, which is equal to p, px, py and pz, and that is equal to minus ih bar del x by del y by del z, and then you know that how it comes out like this, because we have substituted the values or the operator definitions of linear momentum components, and that is equal to minus ih bar del by del x, and then take it out common minus ih bar, and in the bracket is the definition of the del operator, this one. Here you can see that this del operator is actually also called a nebula operator, and it is in 3 dimensions, written as this triangle. This you can see this triangle is actually a nebula operator or del operator, and it is a combination of partial derivatives from all three components. And using this nebula operator, now we can write the angular momentum L in terms of nebula and three components combined, and this is the definition of the angular momentum, total angular momentum then. Okay, so this was sort of first part of the lecture, where you have seen that how the angular momentum is defined in quantum mechanics. And the second one is actually what are the physical properties, interesting properties connected with the angular momentum, and that is the uncertainty principle. Remember that we defined in first part of this course, that is quantum mechanics 1, that the position and momentum are actually not compatible. By this we mean that we cannot with 100% accuracy and simultaneously determine the value of position and momentum, and they are uncertain. Okay, so that mathematically was seen by commutators. We calculated the commutator of position and momentum, and we have seen that it was not equal to 0. So whenever the operator of any two commutator of any two operators is not equal to 0, then it means that it is uncertain. These two values are uncertain. So now in terms of the angular momentum, we would like to see that whether the two components of angular momentum, any two components by the way, of angular momentum are uncertain or not. That is, whether they can be specified with 100% accuracy and simultaneously or not. So to begin with, we would like to calculate the commutator of x component of angular momentum and the y component of angular momentum. I think you can sure do other commutators of other components. Actually, we would do that later, but we can start with any of them, and it's no advantage over doing x and y first. But to start with, we calculate the angular momentum of the commutator of the operator x component and y component of the angular momentum, and we would like to know its value. If this is equal to 0, for example, we will see if it is 0 or not. But if it is equal to 0, that would mean that Lx and Ly, that is the observables associated with the x component of angular momentum, that is the x component of angular momentum, and y component of angular momentum are actually compatible. That is, their values can be determined with 100% accuracy and simultaneously. So both are important: accuracy, 100% accuracy, and simultaneity. So one of them can be sacrificed, one of them can be done with, but when you want both of them together, that is, they are simultaneous and they are with 100% accuracy. So not all of the observables are like this in quantum mechanics. For example, position and momentum cannot be 100% accurate and simultaneously measured. So if Lx and Ly are equal to 0, the commutator equal to 0, mathematically this uncertainty is checked by calculating the commutators. If this is equal to 0, then they are compatible, and if this is not equal to 0, which is actually the case, as we will see, then they are not compatible, and we cannot determine them with 100% accuracy and simultaneously. So now let's do this commutator, and how we do this, as you know, we will use the basic commutator from the quantum mechanics 1 course, where we know that the commutation relation of x and px, that is the linear momentum, is equal to IH bar. I don't need to repeat this, but I will encourage you to kindly do this calculation once again to recall that how the commutators are calculated. Anyway, we will do the first one, this top one over here now, and how we do this is using the definition of the commutator. And what is that? This is to multiply the operator Lx with the Ly from the left first, and then after the minus sign change the order and do this multiplication. So this is the definition of a commutator. And then how the rest of the calculations will go, as you can see that we will substitute the value of Lx, which we have already defined in the previous slide. So Lx we substitute with Lx this one, and Ly with this one, Ly again, and Lx again. And now these two terms contain products, and there could be so many products. For example, this first term going with the first term going with the second with the first, and second with the second, and so on over here. As you can see, all these products. And when you do all these products, what you will get that what you will see that some of them will cancel out because they will be similar and with the opposite sign, so they will must cancel, and the rest of them could be organized in this way. So it's again a simple thing. You can just find out by just looking at them that how you go from here to here. And again there will be one rearrangement again, and this rearrangement will take us here, that is I h bar is xpy minus ypx, and this you can readily identify as the z component of the angular momentum, as we have defined on the previous slide. So what we have seen, this is not equal to 0 actually. This is the lesson, this is not equal to 0, which means that Lx and Ly do not commute. They cannot be specified with 100% accuracy and simultaneously, because their commutator is not equal to 0. It is actually equal to I h bar Lz, and that is another operator. I mean, this can also happen that we don't get an operator, we just get a number, but here we get an operator that is equal to I h bar Lz Lz hat. And if you do repeat these calculations for the other components of this angular momentum, you will find out that all three components do not commute among themselves. For example, Ly and Lz commutator is equal to this thing, and the second one and the third one. So none of them actually commute. So so here you have discovered a three new sets of uncertainty principle, that is any of the components of angular momentum do not commute. They cannot be specified with 100% accuracy and simultaneously in quantum mechanics. So we can write them actually in combined form as well, as you can see over here. This again to check that the component by component come from here, but you can see that the first all L's on the left and L on the right, so you can just imagine that it is true. And in determinantal form, this is again can be written as like the L on the left hand side and the right hand side actually forms a determinant, as we actually started with the in the beginning with this definition for calculation of the components of the angular momentum. Okay. So this was the second part of the lecture. So first part contained the definition of the angular momentum, and the second part actually we have calculated the commutators and seen that none of them equal to 0. That is, the components of the angular momentum do not commute among themselves. So naturally the question arises that can we define some other property or we can construct some other property from angular momentum which actually commutes with the sum or any of the component of the angular momentum? The answer is yes, and that property usually is the square of the angular momentum. So if we define the square of angular momentum, or we construct the square of the angular momentum, we will find out that it commutes with the components of the angular momentum, and it's, by the way, is a very useful property, or a very useful observable in terms of physical meaning. So let's construct this. So the total angular momentum, since is a vector operator, as we know that angular momentum is a vector, so it has in Cartesian components, Cartesian coordinates, three components, that is Lx, Ly and Lz, where Ex, Ey and Ez are just the unit vectors. Remember, these are the unit vectors. In convention we would write I, J and K, but here we have written it Ex and Ey and Ez, and we can form now the square of the angular momentum, that is L square, and L square would be equal to Lx square, Ly square and Lz square, and The next thing is that to check whether this new operator, that is L square, commutes with the any of the components of the angular momentum. And but conventionally we start with the z component, so let's do the z component commutation relation and see that whether Lz and L square commute or not. Since you are already familiar with the commutation relations now, so let's straight go to the calculation, and that is Lz and L square commutator, but L square we can write it into its components form, that is Lx square, Ly square and Lz square. And now you can see these are not just one commutator, but there are three commutators, that is Lz commuting with Lx, Lz commuting with Ly and Lz commuting with Lz. So we would get these three commutators, the first one, the second one, and the third one is by definition equal to 0, because any operator will commute with the with itself or with the square of itself or any function of itself. This we have done in the first part of this course. That's why we get 0 over here, and then we are left with the two commutators. But again, these are not just the two commutators, but these are actually 4 commutators because of the Lx square and Ly square in the second terms of these commutators. And if we open them up, that is we write the Lx as a product equal to Lx square, so we will get two commutator here, that is the Lz commuting with the first Lx and the second Lx going out, and then the Lz commuting with the second Lz Lx and the first Lx going to the left. In the first case it was going to the right, as you can see over here. So we get two commutators from this term, and we will also get two commutators from this term. And if you open up these commutators as we have calculated from our last calculation, and you will get this equation, and if you calculate again this, or you can just look at it, you will see that it is equal to 0. So what we have found, that the square of the angular momentum operator actually commutes with the z component of the angular momentum. That is, they can be specified with 100% accuracy and simultaneously. And same is the case with the others components. For example, Lx with the L square, Ly with the L square, and Lz with the L square will also commute, and combined together we can write them L into L square equal to 0, where L is the total angular momentum now. So now we know that the L square, this new operator, actually commutes with the L, and what would be the possible applications of it? So recall that whenever two operators commute, that is their commutator equal to 0, then they would have a common eigenfunction. And if you recall that whenever operator acts on some function and this function is reproduced again with certain value, for example it's called a, so this is the eigenvalue, so this is the eigenvalue, and this function is an eigenfunction. So when two operators acting on two different operators acting on the same function, like b acting on it again, and we get eigenvalue over here again f, so we see that this f is an eigenfunction of an operator a and also an eigenfunction of an operator b. So that means that it is the common eigenfunction of two operators, and if this is so, then these two operators a and b must commute, that is their commutator must be equal to 0. So since we have seen that Lz square and L square and Lz commute, so therefore they must have common eigenfunction. So let's write that Lz and L square commute, therefore their common eigenfunction is equal to phi Lm, and we will see that this m corresponds to Lz and L corresponds to L square later on. But if they have a common eigenfunction, that this is the eigenfunction of Lz and this is the eigenfunction of L square, then we can write this equation, that is L square acting on phi Lm is equal to phi Lm, and this is the sum eigenvalue. Why this is h bar square L into L plus 1, this you would know into the during the second lecture where we will derive this equation, but at the moment you can just take it as it is and see that this the eigenvalue is h bar square L into L plus 1, where L is some integer going from 0, 1, 2 to the infinity, and Similarly, the second operator Lz also, this phi Lm is also the eigenfunction of Lz. That means that when Lz acting on phi Lm will reproduce phi Lm again, this Lm are just indices, and here the eigenvalue is h bar m, where m is again an integer but now is slightly different integer. It goes from minus L to plus L in an integral steps. Because these are the angular momentum, we will see that in quantum mechanics, when for example electron revolving around the nucleus will have orbital angular momentum and will have spin angular momentum, because in quantum mechanics we have two types of angular momenta, not just one. So these will correspond to them, but this we will see later on. At the moment you can just on the mathematical side you can see that L square acting on phi Lm equal to this one, and this is the just eigenvalue, and Lz acting on phi Lm is equal to h bar m, and this is just the eigenvalue. Okay, now let's understand the meaning of these two equations and start with the first equation. By first equation we mean that as you have seen that L square was equal to, this was the eigenvalue, so L would be equal to h bar L into L plus 1. This is very interesting. Why I say this is interesting? Because the only values an experiment would find for this angular momentum are of this form, and this actually rules out some of the values. For example, one would never find L is equal to h bar into 7 under root. Why? Because there is no integer which gives you 7. If you write this equation, there is no integer for L which gives you this value. You can check it out. For example, try with L is equal to 0, you would get 1 not equal to 7. Try with L is equal to 2, you would get what you would get, 2 plus 1 3, 3 into 2 6, which is not equal to 7, and so on. You try it out, but you will never get any integer which is equal to 7. So it means that this L is equal to h bar 7 under root is not possible. Experiment would never find this value, and this is an experimental check for the correctness of quantum mechanics, that it telling you that experiment would never find this value. And it is so that nobody has done any experiment so far which reports that angular momentum of electron was of this value. On the other hand, you can have value L square 30 h bar square, because you can find an integer L is equal to 5, putting on over here gives you 6 plus 6 into 5 equal to 30. So that's possible, and experiments are done which actually found the electron with L square 30 h bar square. And here you can see that is one of the proofs or direct proofs of the correctness of the quantum mechanics. So then what is the meaning of the second equation? Now we know that L square is equal to 30 h bar square and L is equal to 5. Then what is the value of m, that is the second integer? And we know that it is equal to minus L to plus L, and so L would be 5, so this will be 5 h bar, 4 h bar, 3 h bar, 2 h bar, 0, and so on. So these are just these are actually 11 values. So it means that for L is equal to 5 we can have all these possibilities. We can have all these possibilities. So in other words, these are degenerate, because for just one angular momentum value L is equal to 5, we could have particle, that is electron, in any one of these states. And so we say that there is a degeneracy in our system, and actually it is 11 for or 2L into L plus 1 twofold degenerate. So eigenvalues of L square are 2L plus 1 degenerate values, because their L was equal to 5, so 5 into 2 is 10 plus 1, 11 values we got, by the way, here 11 values. So we say that we have eigenvalues of L square 2L plus 1 degenerate, 2L plus 1 fold degenerate. So this means that we would have 11 states, that is 5, 5, 5, 5, 5, 4, 5, 5, 3, and so on up to 5, 5, minus 5. And these are actually 11 values, and these are all degenerate. By degeneracy, by the way, we mean that when we have for just one angular momentum value, we have these whole set of values, and this creates degeneracy. So for this L square is equal to 30 h bar square. So in today's lecture, to recall what we have done, we have divided this lecture into three parts. The first part was the definition of the angular momentum. The second part was the commutation relations. We wanted to calculate and check the uncertainty principle. And the last part was the degeneracy and the square of the angular momentum constructed to see that if we can have some property which is commuting with the any component of the angular momentum. So by this I hope that you have got the value of angular momentum in quantum mechanics, and I thank you all.